So we got a big video today. We're going to look at the Fundamental Theorem of Calculus, parts 1 and 2. So this links together the notions of integration and differentiation. And we're going to be using the formalism for integration that we have defined and looked at throughout the past couple of videos. Let's recall a couple of equivalent formulations of Riemann integrability. So a bounded function f from ab to r, that closed interval ab, is Riemann integrable if and only if, for every epsilon bigger than 0, there is a partition, which we could call p epsilon of ab, such that the upper sum of f on that partition minus the lower sum of f on that partition is less than epsilon. The upper sum is always bigger than the lower sum, so this is pinning this difference between 0 and epsilon. So in other words, like that's getting quite small. These two are trending to the same number. But that's equivalent to the upper integral of f being the same as the lower integral of f. And in that case, we say that that's just equal to the integral of f on ab, which we denote with this like standard calculus notation. And I'll let you guys check in the previous videos for what the upper and lower integral are, but the upper integral is essentially the infimum of all of the upper sums as you range over all possible partitions. And the lower integral is the supremum of all of the lower sums as, again, you range over all possible partitions. Then finally, there's a sequential criterion for integrability that's given like this. So this is if and only if there is a sequence of partitions Pn of the interval AB such that this limit as n goes to infinity of UFPn minus LFPn is equal to 0. So notice, if you've got this sequence of partitions Pn, then that gives you this sequence of numbers, which is this difference of the upper sum on that partition minus the lower sum on that partition. So that difference of numbers is trending towards 0. So check it out. We've got 1, 2, 3, 4 formulations of integrability. So that's nice. Okay, so now we're going to prove Fundamental Theorem of Calculus part 1. And so this says that if we've got a function f from ab to r and it's integrable, so in the background we're assuming that it's a bounded function, and capital F from ab to r satisfies the rule that f prime capital F prime of x equals little f of x for all x in ab. So in other words, it is an antiderivative of little f. Then the integral of f over the interval ab is equal to capital F evaluated at b minus capital F evaluated at a. So obviously you guys are probably pretty familiar with the Fundamental Theorem of Calculus because generally a calculus type course is taught much before a real analysis type course, and you do a bunch of examples of this kind of stuff before looking at these formal kind of ideas. But here we're gonna prove this theorem using this formalism that we've derived in the last several videos. Okay, so let's maybe get to it. So let's suppose that P, and we'll say that P is equal to x0, x1, all the way up to xn, is a partition of our interval a comma b. Great. And so let's see what that gives us. So that gives us a couple of things for free. So notice that gives us that x0 is equal to a. And then that's going to be less than x1, which is less than x2, all the way up to less than xn, which is less than xn, which is equal to b. I should have said less than xn minus 1 there. So it's just a finite sequence of increasing numbers starting at a and ending at b. So that's what we're using for the definition of a partition of this interval. Okay, so next we're going to apply the mean value theorem to each of these subintervals, which is constructed out of this partition. So let's say we'll do that. So apply the mean value theorem to each subinterval. So maybe we'll denote it by xi minus 1 to xi, and we'll say, notice that this is a subinterval of a, b. Great. So what that does is brings into existence some sort of, let's call it maybe yi in the open interval xi minus 1 and xi, such that we have the following setup. So we'll have capital F of xi minus capital F of xi minus 1 over xi minus 1 is equal to capital F prime of yi, which that is little f of yi. Great, so we've got something like that. Now next what we want to do is notice that we can retool that a little bit, and we will write this like capital F of xi minus capital F of xi minus 1 will be equal to little f of yi times xi minus 1. So that's going to be for some yi between xi minus 1 and xi. Now, since yi is on the subinterval xi minus 1 xi, we know that f evaluated at yi is going to be between the infimum of all of the values of f on that subinterval and the subprimum of all of the values of f on that subinterval. So let's maybe point that out over here. So we have little mi is going to be less than or equal to f of yi, which is going to be less than or equal to capital Mi. Where we're using that same notation that we did in previous videos, let's maybe write it in here. So we have little mi is the infimum of little f of x as x runs through everything on the subinterval xi minus 1 to xi. And then capital Mi is the subprimum of f of x on that same subinterval. So by the definition of the infimum as the greatest lower bound and the subprimum as the least upper bound, well, that means that in particular they are lower bounds and upper bounds, which puts any value of the function strictly between them. But now what we'll do is multiply both sides of this inequality by xi minus 1. So that's going to give us little mi times xi minus 1 is less than or equal to f of yi times xi minus 1. But notice, by our mean value theorem construction, that's equal to this capital F of xi minus capital F of xi minus 1. So that's the version of that quantity I'll put here. And that's the most important step. And then that's going to be less than or equal to capital Mi times xi minus 1, like that. Okay, nice. Now what we'll do is sum over all I between 1 and n. But notice, summing this left-hand part of the inequality over all I between 1 and n gives us the lower sum of f on this partition. Summing the capital Mi, or in other words, the right-hand side of this inequality over all of these I, gives us the upper sum of this function on this partition. And then in the middle, we'll just write down what that is. That's going to be the sum as I goes from 1 to n of capital F of xi minus capital F of xi minus 1. Okay, so let's maybe bring this inequality up and we'll move on to finish this part off. So far we've taken the partition P, which are the points x0 to xn of our interval AB, and via the mean value theorem, we argued that the lower sum of f on this partition was less than or equal to the sum as I goes from 1 to n of this capital F of xi minus capital F of xi minus 1, which was less than or equal to the upper sum of this partition was less than or equal to this upper sum of f on the partition P. So this middle sum telescopes, which is maybe not so hard to see, but let's maybe look at all the details just for completeness. So let's go ahead and expand this into the sum as I goes from 1 to n of f of xi minus the sum as I goes from 1 to n of f of xi minus 1, like that. Okay, good. Now next what I want to do is maybe re-index this second sum so that these two terms look the same. So let's see how we can do that. We can replace I with I plus 1. So if we replace I with I plus 1 here, well, what does that mean? Well, when I plus 1 equals 1, I is equal to 0. So that's going to mean that this starts at 0. When I plus 1 is equal to n, that means I is equal to n minus 1. So this is going to end at n minus 1. And then if we've got I minus 1 and then we change it to I plus 1 minus 1, then we're going to have f of xi like that. Okay, good. But now these are indexed in a way that we could combine them nicely, but they have different amounts of terms, or they have the same amount of terms, but they have slightly different terms. So notice this one ends at I equals n, but starts at I equals 1. This one ends at I equals n minus 1, but starts at I equals 0. So let's go ahead and pull out the first term from here. So that's going to be f of x sub n, and we're going to have plus this sum as I goes from 1 to n minus 1 of fx sub I minus this sum as x goes from 1 to n minus 1 of fx sub I. And now we're going to pull out the first term from here, so that's going to be minus fx0, like that. But now we see that this sum and this sum are exactly the same. And then furthermore, because of the structure of our partition, we know that xn is equal to b and x0 is equal to a. So that means we can replace this with b and this with a. So this whole middle part collapses to f of b minus f of a. So let's maybe go ahead and insert f of b minus f of a to this middle part where this sum is, and then we'll argue the rest. Okay, so we just argued ourselves down to the following inequality. And this is true for any partition at this point. We have the lower sum of f on that partition is less than or equal to f of b minus f of a, which is less than or equal to the upper sum of f on that partition. Okay, so now what we'll do is take a sequence of partitions, Pn, such that the limit as n goes to infinity of uf Pn minus Lf Pn is equal to 0. But what follows from that is that the limit as n goes to infinity of Lf Pn is equal to the limit as n goes to infinity of uf Pn, which is equal to the integral itself. So this doesn't follow exactly from all of the statements over here. Well, it does follow from the statements over here, but it isn't explicitly stated. The fact that this limit is equal to 0 doesn't mean those two limits even exist. But suffice it to say they do exist and they're equal to the integral themselves. So now what we'll do is put this sequence of partitions into this inequality. So that means we have LFPN is less than or equal to FB minus FA, which is less than or equal to UFPN. Now we can take the limit of the left and right hand side of this inequality. So the left hand side of this inequality is trending to the integral from a to b of f. The left hand side is also trending to the integral from a to b of f. But that means this center thing is equal to the integral from a to b of f by the squeeze theorem. Notice that this is straight equal to it. We don't really have to take a limit because there's no dependence on the partition in the middle there. But that finishes the proof of the FTC part 1. Okay, so let's maybe get rid of this and we'll look at the FTC part 2. Now we're ready to look at the Fundamental Theorem of Calculus part 2. So let's assume that we've got a function little g from a, b to r, and it is integrable. And then we'll define this function capital G of x, which is the integral from a to x of g. And this is going to be for all x on that closed interval a to b. Then two things will follow. So first, g will be continuous on a, b. And then next, if little g is continuous at c between a and b, then capital G is differentiable at that point, and furthermore, the derivative of capital G at c is equal to little g at c. So generally in a calculus class, you only really look at this second one because it tells you how to take derivatives of these weird functions defined in terms of integrals, but we'll prove both of them. Okay, so let's maybe get to proving this first one first. In other words, we want to prove that G is continuous on AB. So let's go ahead and take x, y somewhere on the interval AB, like that. And then next, we want to look at the absolute value of the difference of g of x and g of y. But notice, by our definition of capital G, that's going to be the absolute value of the integral from a to x of little g minus the integral of a to y of little g. And you know, while we're at it, let's maybe put some sort of ordering. Let's say that x is going to be less than y. So we've got something like that. But now we know some properties of integrals. And we know that we can mash those two integrals together using those properties, and that's going to give us this absolute value of the integral from x to y of g. Great. And then next, what we will do is bring that absolute value inside the integral by like an integration version of the triangle inequality. That's going to be less than or equal to the integral from x to y of the absolute value of g. Okay? But next, that's going to be less than capital M times the absolute value of x minus y, where capital M is equal to the supremum of g of t as t ranges over this interval x to y, like that. Okay, so again, this isn't explicitly written up here, but we're only really talking about integrability of bounded functions in this setting. So we can always find a supremum of this function g. It's going to be bounded on this interval x to y for sure. Okay, great. But now let's notice that we've got this left-hand side and then this right-hand side. And that actually shows that this function is indeed uniformly continuous via the Lipschitz condition. So this is the definition of a function being Lipschitz. But then it follows very, very quickly that this thing is uniformly continuous. So generally that's given as like an exercise in a course like this in the past. So I'll let you guys check the notes to see if you've done that, or maybe you can just prove it from here. But let's maybe sketch the end. So this means that capital G is Lipschitz, but then that means that capital G is uniformly continuous. But uniform continuity is like a beefed up version of continuity, so that means it's continuous. Okay, so we've proven part one. Now let's go ahead and get rid of this and we'll move on to part two. Okay, now let's look at this second little bullet point, and that says that if G is continuous, little g, at C between A and B, then capital G prime is equal to little g. Built into that means that capital G is differentiable. So remember that the differentiability condition is essentially just saying that this G prime exists in terms of the limit. So this limit is equal to the limit as x goes to C of g of x minus g of c over x minus c, like that. So let's maybe go ahead and look at what this means. This is going to be the limit as x goes to c of 1 over x minus c. And here we're going to have the integral from a to x of little g minus the integral from a to c of little g, just by the definition of our capital G. But now we can use, again, properties of integrals like we did in the last case to smush those together. That'll give us the limit as x goes to c of 1 over x minus c. And then we've got this is times the integral from, let's see, maybe c to x of little g, like that. So now that actually tells us that this is the type of object that we need to be looking at. And our goal, so let's maybe put that over here in yellow. So our goal is for this to be equal to g evaluated at c. So we can prove that with an epsilon delta type proof of a limit. So let's maybe go ahead and say that we have some arbitrary epsilon bigger than 0, and the type of quantity we want to look at is the absolute value of this guy over here minus this guy over here, and we want to make that as small as possible. So let's see if we can do that. Absolute value of 1 over x minus c times the integral from c to x of, now I'm going to put g of t dt in here just so that we can kind of see what's going on a little bit easier. And then this is going to be minus g of c, like that. So again, this is what we want to make small. Okay, so now we're going to start putting this together. So I want to notice that I can multiply this by x minus c and divide it by x minus c. I'll divide it by x minus c just by putting 1 over x minus c, and I'll multiply it by changing this to the integral from c to x of g of c. Notice that's equivalent to multiplying and dividing by x minus c. But that allows us to push that together. So we can push that together into an integral, whereas this g of c was outside of the integral before. And also we can bring the absolute value inside by applying like the triangle inequality involving integrals. So this is going to be less than or equal to 1 over x minus c. And then we've got the integral from c to x of g of t minus g of c. And then this is going to be all dt, like that. And next we can get to our choice of delta and stuff. So now at this point, we're going to choose a delta bigger than 0 so that the absolute value of g of t minus g of c is less than epsilon. We're kind of motivated by that at this point because that's what we see inside of the integral. And that's possible, again, because little g is continuous, which we're assuming at the beginning. So that means this is going to be less than or equal to 1 over the absolute value of x minus c, and then we've got the integral from c to x of epsilon dt. Good, and then that, again, we know what the integral of a constant function is. This is just the constant function epsilon. So that's going to be epsilon times x minus c, but that's going to cancel the x minus c, just giving us epsilon. So let's see what we've got. We've got this quantity right here, minus g of c, can be made as small as we want. But how small do we want it? Well, we want it to be within epsilon, but then that tells us that g prime of c is equal to little g of c as needed. And I just noticed that should be a strict inequality. And that's a good place to stop.